So the next important concept, important thing you should know is the concept of a conditional probability. So what a conditional probability is. So the conditional probability of A given B is the probability of an event A given that event B has already occurred. So the experiment is already done. But outcome, you don't know the outcome exactly. You have some partial information about outcome of the experiment. You know that some event B has already occurred, but you don't know the outcome itself. You only know the fact of the occurrence of some event based on this experiment. And this may affect probability of other events based on the same experiment. So ordinary unconditional probability of event A can differ from conditional probability when there is additional information about the occurrence of the event B. For example, let's say that our experiment is when we go out to the street and look at the first person we meet there, and event A, for example, is that this person is male. So if we assume that half of all people in the street are male and half are female, then probability of this event A is 1/2. But now let's say that, for example, event B is that this person, the first person we meet, is a bearded person. So it has beard. And in this case, if we know that event B has already occurred, then probability of A is 1 or almost 1. So if someone tells you, he tells you, I just went out to the street and I saw a person, and this person has beard. So what is the probability that this person is male, in your opinion? So you say this probability is equal to 1. And if you have know this information about his beard, you would say that this probability is 1/2. So that is how a conditional and unconditional probability can be very different from each other. So how conditional probability is defined mathematically? Mathematically, P of A given B is P of A intersection B divided by P of B. So probability that both events will occur divided by the probability that B will occur. Or if you want to find this probability using discrete uniform probability law, so you want to find it basing on the outcomes of the experiment, you can say that P of A given B is equal to number of outcomes favorable for both A and B, favorable for the intersection of A and B, divided by the number of outcomes favorable for B. While calculating conditional probabilities, we are to be very careful, because wrong understanding of what is happening can lead us to serious mistakes. Let me show you an example. Suppose that I have a colleague and I know that he has 2 children, and I know nothing about the sex of his children. And this colleague of mine invites me over, and I come to his house and I knock on the door, and one of his children opens me a door, and this is a boy. The one who opens the door is a boy. What is the probability that the other child is also a boy? One may think that, so obviously 1/2, because sex of the other child does not depend on the sex of the first one. And actually this is the right answer, but let's do all necessary calculations properly. What is the sample space for this experiment. Actually, what the experiment itself is. Let's say that the experiment is that this colleague of mine and his wife, they decided to give birth to 2 children. And so this experiment has 4 possible outcomes, namely girl, 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 boy, boy, girl, and boy, boy. So these are my little omegas, outcomes of the experiment. One may ask, why do you separate these 2 outcomes, girl, boy, and boy, girl? This is actually the same. One of the children is a boy and the other one is a girl. This is just one single outcome. But if I want to apply discrete uniform probability law, I can do this only if I have an experiment with its outcomes being equally likely. So I need an experiment such that its outcomes are equally likely, and if I unite these 2 outcomes into a single one, so these 3 outcomes won't be equally likely. So that is why it's better to separate them. And let's say that probabilities of these 4 outcomes are 1/4 for each one. So what are our events of interest? The first one is the event that has already happened. What has already happened? The child who opened the door for me is a boy. So that means that at least one of his 2 children is a boy. So this event has already happened. Let it be event C. So at least one is a boy. And then I'm interested in probability of another event, in probability that the other child is also a boy. So that means that both are boys. This is event A. Both are boys. Now, which outcomes are favorable for the event C? All except for the first one. So I can say that outcomes omega 2, omega 3, and omega 4 are favorable for the event C, and so NC is 3. Then, how many outcomes are favorable for A? Only 1. And for A intersection C, also only 1. A intersection C means that at the same time, at least one of them is a boy and both are boys. So only one outcome, omega 4, is favorable for this event. And so N A intersection C is 1. And according to our formula, I can say that P of A given C is N A intersection C divided by N C 1 divided by 3, 1/3. Not 1/2, but 1/3. So, seems to be very strange. So probability, according to these calculations, probability that another child is also a boy is not 1/2, but 1/3, after we know that the first one is a boy. So where is the mistake here? What is wrong? Actually, I was wrong from the beginning when I described my experiment. So what I have said, I said that the experiment is that my colleague and his wife give birth to their 2 children. But actually, this is not the experiment that actually took place. The experiment is me knocking on the door and one of his children opening the door for me. This is the experiment. And so what is the sample space? The sample space, so what are the outcomes, possible outcomes of this experiment? So here, I think that, for example, the first child is the elder one and the second is the younger one. But I should divide them not by their age, but I should take into consideration who opened the door for me and who is the other one. So, actually, this experiment also has 4 possible outcomes, and these outcomes are: the first one, the one who opened the door for me is a girl who has a sister. Another outcome, the one who opened the door for me is a girl who has a brother. Or it can be a boy who has a sister, or it can be a boy who has a brother. So the first one is the one who opened the door for me, and the second one is his or her sibling. And so this is the true sample space of the experiment that takes place here. Mm-hmm. So, and now, what are our events of interest? So, event that has already happened is that the child who opened the door for me was a boy. So, a boy opens the door. This is the event that has already happened. And event of interest A is both are boys. And we can see that, so outcomes favorable for the event C are omega-3 and omega-4. There are only 2 outcomes favorable for C. And for both A and C, as in previous case, only omega-4 is favorable. So conditional probability of A given C is is 1/2, as here we have 2 favorable outcomes and here 1 favorable outcome. So correct understanding of what is happening, of the structure of the sample space, gives us the correct answer. And if we don't think before our calculations, we can get something very strange as we have here. Another couple of definitions. What are disjoint events? Disjoint events are such events that they cannot occur at the same time. So if the experiment is done, either A can occur or B, but never both. We cannot see such a repetition of our experiment that results in occurrence of both A and B. For example, if you roll a dice, event A is even number and event B is an odd number. And so these events A and B are disjoint ones because so the number cannot be even and odd at the same time. Mathematically, disjoint events can be defined as such events that intersection of A and B is an impossible event. So their occurrence at the same time is an impossible event. It never happens. Another important property of random events is their independence. So how independence is defined mathematically? Two events, A and B, are called independent events that if the probability of their intersection is equal to the product of their probabilities. So probability that A and B will occur at the same time is equal to P of A times P of B. If it is so, A and B are independent. So if this equality is not true, if probability of A intersection B is not equal to P of A times P of B, they are not independent. What is the physical sense, physical meaning of independence? Actually, this means if two events, A and B, are independent, that means that occurrence of A doesn't give you any information on B. So if you know that A has already occurred, it doesn't change probability of B. It doesn't change your thoughts about B. So, and vice versa. If you know that B has already occurred, it gives you no information on A. So, if we'll go back to our example with the first person we meet at the street. Let event A be that this person is male, event B be that this person has beard, and event C is that this person has glasses. So we can see that events A and B are not independent, because if you know that someone has beard, probability that this person is male changes dramatically. And vice versa, if you know that someone is male, probability that this person has a beard also changes. Not so strong, but still changes. But if you are told that someone has glasses, it doesn't tell you anything about whether this person is male or not. And vice versa, if you are told that someone is male, it doesn't tell you anything about his glasses or her glasses, so you don't know, and the probability of this person having a glasses doesn't change anyhow. So that is how you can understand if the pair of events is independent or not, just basing on physical sense of this concept. Sometimes you are given that a pair of events are independent, and so after you know this, you can say that P of A intersection B is equal to P of A times P of B if you need. And sometimes, vice versa, you are asked if these two events are independent or not. And so in this case, you are to check if this equality is true or not in your case. So let's solve an example. Let's say that I have a deck of 36 cards and I choose one card at random. This is my experiment, and I have two random events based on this experiment. Event A, chosen card is a king, and event B, this card is of diamonds. So the question is, are these two events independent or not? Just from the point of view of our just common sense, we can say that they are not independent. Why? Because if you are told that chosen card is a king, it tells you nothing about its suit. And if you are told that chosen card is of diamonds, it tells you nothing about whether it is a king or not. So occurrence of each of these two events give you no information about the other one. So that is why they are independent. But if you are asked such a question, I mean, whether these two events are independent or not, so you are to do all necessary calculations to check if this equality is true or not. So I am to find three probabilities, P of A, P of B, and P of A intersection B. Let me do this. In our case, this is very simple. So as P of A is number of outcomes favorable for the event A. How many kings I have in a deck? 4 kings. So number of outcomes favorable for A is 4, divided by the total number of all possible outcomes, that is 36. So P of A is 4 divided by 36, it is 1/9. Then P of B, 1/4 of all cards are of diamonds, so 9 out of 36. And probability that this card is a card of diamonds is 9 divided by 36. That is 1/4. And as for the probability of A intersection B, this is number of outcomes favorable for both A and B. So favorable for this event, A intersection B. Actually, what is A intersection B? This means that both are to occur, to happen. So that the chosen card is a king, and at the same time it is a card of diamonds. So A intersection B means king of diamonds. And there is only one king of diamonds in a deck, so only one outcome is favorable for this event, and total number of outcomes is the same, 1/36. So what do we see? P of A intersection B is equal to 1/36. P of A is 1/9. And P of B is 1/4. And we see that 1/9 times 1/4 is equal to 1/36. So this equality is true. And that means that events A and B are independent. So because of this fact, because P of A intersection B is equal to P of A times P of B, A and B are independent. So this is the usual way to answer a question. Are the two random events independent or not? Let's now consider a little bit more complicated example with 3 random events. So, suppose that we have 3 balls. The first one is black, the second one is white, the third one is red, and the fourth one is of 3 colors. It is partially black, partially white, and partially red. And these 4 balls are inside of a box, and I choose one ball at random. And so this is my experiment. And there are 3 random events based on this experiment. Event A, there is a black color on the ball I have chosen. So there is black color. Event B, there is white color. And event C, there is red color. There is black, white, and red color respectively on the surface of the ball I have chosen. So let us find probabilities of these 3 events. So this experiment has 4 possible outcomes, as I have 4 balls. So n, number of all possible outcomes of the experiment, is equal to 4. And so number of outcomes favorable for event A is 2. So as this ball has black color and this one also. So NA is 2. So P of A is 2 over 4, 1/2. The same for events B and C. So number of outcomes favorable for B is also 2, as this ball and this one have white color, and that is why P of B is also 2 over 4, also 1/2. And C is also 2, as this one and this one have red color, and so P of C is 2 over 4, is 1/2. Then let's find probabilities of intersections. So P of A intersection B. So probability that the ball that is chosen has both black and white colors. So there is only one outcome favorable for this event, this ball of mixed color. So that is why probability is 1 over 4, probability of A intersection B. So as only one outcome is favorable for this event. So the same is for P of A intersection C. So only one ball has both black and red colors, 1 out of 4. And the same is for intersection of B and C. It is also 1/4. So what can I say? So after having these 6 probabilities, so P of A intersection B is equal to P of A times P of B. That means that A and B, events A and B, are independent. So the same is for A and C, for B and C. So we see that, so this probability is 1 over 4, and this 1/2 and 1/2. So for the same reasons, A and C and B and C are also independent. So A and C are independent, and B and C are independent. So we can say that these events are pairwise independent. Pairwise independent, that means that any pair of these events are independent events. So A and B, A and C, B and C, we have 3 pairs, and all 3 pairs are independent. So they're pairwise independent. And what about their independence as a whole? So are these 3 events independent? So what should I find to understand? Is it true or not? So I need probability of their triple intersection. So probability of A intersection B intersection C. So probability of A intersection B intersection C is a probability of getting a ball that at the same time has black and white and red color. So there is a ball of this kind, just one of them. So probability of this event, A intersection B intersection C, is 1/4. And if I multiply P of A, P of B, and P of C, that are all equal to 1/2, I'll get 1/8. And so there is no equality here. So what I can say that these 3 events, A, B, and C, are not independent, as P of A intersection B intersection C is not equal to P of A times P of B times P of C, but in spite of this fact, they are pairwise independent. So any pair is a pair of independent events. So there is a difference between independence of a group of events and pairwise independence of the events that are in this group.